For thousands of years, our ancestors have worshipped and observed the moon and its motions with extraordinary precision, building huge monuments of stone, earth, and wood to memorialize even the most subtle attributes of lunar motion. It is an ongoing mystery as to why ancient peoples all over the world were such dedicated, even obsessive observers of the moon and its cycles. One might assume that modern scientific research would demystify the moon, its origin, and its properties. However, the opposite has happened. The more we learn about the moon, the more mysterious it becomes. Join us as we take a dive into the high strangeness of our nearest celestial neighbor. I'm Randall Carlson, and this is the Squaring the Circle podcast. Well, I'd welcome everybody to another episode of Squaring the Circle, where myself and my colleague John Arthur Fiallo have been discussing our nearest neighbor, the moon, and learning about it. And what we're finding, in my mind, is pretty darn interesting. I'm still trying to sort out all of the things we've been talking about. We've talked about the apparent extraordinary rigidity of the crust, as would seem to be reflected in the ability of the crust to withstand gigantic impacts. We talked about cratering on the moon, the ratio of width to depth. And we learned that there seems to be a threshold at which the width of craters can continue to grow larger and larger, but the depth seems to max out somewhere around 3 to 4 kilometers. In fact, it was said in one of the articles we referenced that some of the larger mare basins, if you're standing at the center, you don't even see the relatively large mountain ranges that form the rims of the craters. So that's an interesting phenomena regarding the moon. Then we talked about some of the lunar transient phenomena, which seem to suggest activity. And what kind of activity? The assumption has been for years that the moon was geologically a dead object. But if that's the case, then how do we explain the lunar transient phenomena? And we got into it. I think we covered it most. Maybe there was a few things to pick up the thread of our discussion. This was, this was published back in 1991. Okay, so this was Winifred Sawtelle Cameron, published in Sky and Telescope. About 200 of some 30,000 lunar features visible in telescopes have been recorded as lunar transient phenomena, or LTP sources. Half have shown activity only once. Of the remainder, a mere dozen features contribute to 3/4 of all reports. One area, the Aristarchus Herodotus Schroeder's Valley, is responsible for fully 1/3 of the total number cited. Most LTP activity occurs along the edges of Maria, near volcanic features like domes, sinuous rills, and craters with dark halos or floors. But these regions, like the rest of the moon, have been considered geologically dead. So we did discuss that, we did quote that, but it's a good place to pick up our discussion. So what do we attribute this to? Is it volcanism? Is it, if it's not volcanism, what could it be? We did see that there was evidence of outgassing of carbon gases, and water vapor. And we saw the one quote by, I think it was Farouk El-Baz, wasn't it? He said that if the observation is confirmed, are considerable. If water vapor is coming from the moon's interior, says lunar scientist Farouk El-Baz, this is serious. It means that there is a drastic distinction between the different phases in the lunar interior, that the interior is quite different from what we have seen on the surface. Well, We'd also discussed the density of the moon, and we discussed why that was anomalous. And essentially, we learned that the overall density of the moon as a whole, 3.34 grams per cubic centimeter. Well, what's interesting about that? Well, that's pretty low density. And in fact, that is roughly the density of a normal rock you would pick up on the surface of the Earth, and the density of rocks, basaltic rocks, picked up on the surface of the moon. So what this is implying is that the material forming the surface doesn't seem to be less dense, or let me turn it around. The material forming the interior of the moon doesn't seem to be more dense than the material forming the surface of the moon. Now, how do you explain that? That's one of the things I've been puzzling over for a long time. How do you explain this uniform density? Now, one could assume from that that implies that the moon as a whole is a homogeneous body. But then that raises difficulties in itself, which we'll come back to in a few minutes when we start discussing Mascons. You know, we're at the point of Apollo 11 convinced that there was really no water because they didn't see the hydrous minerals that one would expect to find, those that contain OH radicals in the samples. So then, they believed, so it was John W. Freeman Jr. and H. Kent Wells of Rice University in Houston that announced what they believed that they had detected water vapor on the moon using the suprathermal ion detector experiment. We talked about that. The SIDES, which is the acronym SIDES, have been quietly monitoring clouds, in quotes, of low energy ions during the lunar day and before sunrise and sunset. Okay, ions thought to have escaped from the Earth's magnetic bow shock wave and ions from man-made impacts, lunar landings, and liftoffs. But then it was on March 7th that the instrument saw something unusual at the 14 site. Let's see, that would be right here. A very high flux of ions in the spectrum predicted for water vapor. Apollo 12 SIDE also detected the ions. The flux of 783 counts per 1.2 seconds was much higher than anything seen before, more than 100 times greater than that detected when the lunar module vented. Another unusual aspect of the detection was that the flux occurred at the same time that swarms of moonquakes were detected, rumblings that lasted from 12 to 14 hours. The ion occurrence began shortly after the moonquakes began and stopped shortly after the quakes ceased. Freeman speculates that water vapor could have come from a fissure created by the quakes. And, says Hills, the findings would not contradict the lack of water and materials found at the surface if the vapor were coming from deep within the interior. Well, then, as Farouk says, that would be considerable. What in the world does that mean if there's water inside the moon?
Well, the question comes is, how is it forming? Where's the water, and where are these other volatiles coming from? If we have carbon, hydrocarbons or carbons being formed inside, can the moon be geologically dead?
It would seem not.
Raises the question.
Right. I'm going to pause for just a minute to talk about our partners over at Shippo, who may save you a significant amount of headache in your day-to-day business. We sell a variety of geometry tools and models, like our beautiful platonic solids here at Randall Carlson LLC. And when it comes to managing shipping, e-commerce, and returns, we've been using Shippo for over 4 years now, and we're very pleased with their service. Shippo's interface is intuitive, the primary order page is easy to navigate, and we have enjoyed stellar technical support. If Shippo can help you with your needs, please use the code below to partner with a great company while supporting our work here at Squaring the Circle. Thanks, and now back to the show. Then we also noticed that that they seem to be concentrated around certain features. One in particular was the crater Aristarchus. The Apollo 11 command module had just achieved orbit around the moon when the Mission Control Center in Houston, Texas received word that amateur astronomers reported transient phenomena in the vicinity of the crater Aristarchus. Asked to check out the situation, astronaut Neil Armstrong looked out his window toward the Earth-lit region and observed, quote, an area that is considerably more illuminated than the surrounding area. It seems to have a slight amount of fluorescence to it. Let's look in fluorescence. Let's look into that a little deeper. Let's look up fluorescence and see what we can learn about fluorescence.
Well, you're looking at something that is going to be a lot like your fluorescent light. It is illuminating based on some sort of arc, usually, or there's some sort of chemical, electrical cause. And so, real quick, some fluorescent material examples here. Let me pull that up. You're going to have something that looks, usually when you're talking about TLPs, it's a red or an orange fluorescent light.
Mm-hmm.
Now, these are rocks. Okay, these are people, fluorescent.
Those were people, not
correct.
rocks.
Those are people. Okay. Correct. Right. Correct. Matlaline, I guess, is a fluorescent substance in the wood of the tree. I'm not going to try to pronounce that Latin. I'm going to move forward. But when you're looking at something that is fluorescent, it is going to be usually lit electrically or chemically. So where are we getting that light on the surface of the moon?
Well, that's what I'm wondering. Why are we getting...
Is it electrostatic? Is it electrochemical? Or is it an arc? Or is it volcanic? Or is it something else?
Well, I don't know, but I'm getting awfully darn curious about this whole thing.
None of this should really be happening unless, of course, the moon isn't geologically dead. And I think that's something that, if you want, right now, we can pull up that video from NASA. They actually...
Let's do.
Actually did a little bit of research here. And what we're going to look at some geological evidence on the moon for specifically why the moon may not be as dead as we think.
2 years ago, we reported evidence that the moon is shrinking. Now we've found evidence that the moon is actually being pulled apart, forming features called graben. So the shrinking moon, it turns out, is not shrinking everywhere. Some places the moon is actually expanding by a little bit. So finding these young graben was a real surprise because we thought, well, all these lobate scarps are telling us the moon is shrinking. So what are these little small graben that are telling us the moon is pulling apart doing in this picture? How does this all fit together? All that's related to how the moon has evolved, how the moon has lost heat over its 4.5 billion year history. Most of the terrestrial planets, when they formed, were very hot, and they got so hot that they actually completely melted. When that happens, they will be in a general state of contraction because they're still hot on the inside and cooling down, and as they cool, they want to shrink. Only the outer part of the moon melted, forming what is called a magma ocean. And in that model, the balance of stresses or forces that are acting on the moon would allow us to form both these small lobate scarps that show contraction as well as these small graben that show the moon being pulled apart. One of the really, really exciting returns of the Lunar Reconnaissance Orbiter mission is that we've seen this now growing evidence of very young geologic activity on the moon. Many, many people have felt that the moon was pretty much geologically dead, and what we're finding is that that's totally wrong, that the moon appears to be geologically active now.
Interesting.
Yes. And I hope the second Artemis mission doesn't get pushed off too far.
Me too.
Yeah.
Me too. NASA keeps getting axed for no good reason.
For no good reason, right.
But that is interesting because, again, until recently, until the LRO's mission, we really didn't think that the moon was geologically active. Now, if there is a hot core on the moon, that immediately throws a huge question, because is the moon homogeneous if it has a hot core? By definition, it can't be.
It can't be.
It can't be that 3.4 number in density. It can't. It can't.
Well, if you have a denser lunar core, the denser the lunar core, the more mass there is in the core, the less mass there has to be between the core and the surface of the moon.
Correct. Because we actually have the rough weight of the moon calculated, the rough mass.
Yeah,
so
we actually...
It was 73 million.
I think it was 73 trillion.
Trillion.
Yeah.
Yeah. Heavy.
Yeah.
73 trillion kilograms, right? Was it kilograms or pounds? Remind me.
I think it was tons.
Tons. 73 trillion tons.
Tons, yes.
I'm going to look that up. Yep. 73 trillion kilograms. 73 trillion kilograms. This is a lot of kilograms.
Yes, I would say so.
So, with that said, if we have a hot internal core and our mass at the surface is roughly 3.4, it would have to be 3.4 the whole way through. There's something going on in the moon. And so there's a few different explanations. Lava tubes, but also that doesn't account for impact craters.
Right. So maybe we should talk about the Mascons.
I think we should, because that rolls right into Mascons.
Well,
Because the moon's not homogeneous. What is a Mascon, Randall?
Well, that's a contraction for the term mass concentrations. Mascons, which are lunar mass concentrations. The lunar orbiter missions have provided both high-quality photographs of the moon and supplementary scientific information concerning the gravitational field of the moon. Previous investigators have concluded that the moon was gravitationally rougher than anticipated. Something else that was not anticipated. The roughness of the moon has been of interest to the Apollo project because of the resulting perturbations on the trajectory of the Apollo orbiting spacecraft. For these reasons, a new analysis has been done with the use of the accurate tracking data received here by the NASA Deep Space Network, operated by the Jet Propulsion Laboratory. We now report that this new processing of the lunar orbiter data has produced unexpected results. So this is back in 1968. Now, there's been nothing in the ensuing decades that has debunked any of this. I mean, the Mascons are fully accepted as being real on the moon, still are. I don't think the explanation, nobody's settled on the explanation for Mascons. But let's look a little further into it here. The study of local accelerations on the spacecraft resulted in a gravipotential map of the lunar near side, which has revealed very large mass concentrations beneath the center of all 5 near-side Maria, which is Imbrium, Serenitatis, Crisium, Nectaris, and Humorum. In addition, they were observed in the area between Sinus Estium and Sinus Medii, and Mare Oriental, or Oriental. The large rate of change in the accelerations over these Mascons reveals the relatively small physical extent, which is 50 to 200 kilometers, which would be about 30 to 120 miles, roughly, from 30 miles wide to 120 miles wide. In fact, analysis of the detailed computer results indicates a non-spherical trough-like mass distribution, approximately 50 by 200 kilometers, running generally east-west in Imbrium and Serenitatis. So literally, what happened is as the lunar orbiter is going over the surface, there were points where the gravity of these Mascons was so strong that the lunar orbiter dipped. It actually took a dip in its orbit.
Terrifying for them.
Probably so. Then, even though we have computed both masses and depths for the largest Mascons, nevertheless, our present quantitative data require further refinements. One may easily compute approximate masses from an assumed depth, such as 50 kilometers. Okay, so they're assuming for the purposes of calculation that this, whatever this mass is, 50 kilometers, 30 miles deep. The Mare Imbrium Mascon yields numbers of the order of 20 times 10 to the negative 6th lunar masses. Well, you don't need to worry about that too much. It just means, negative 6, which is 1/millionth, 20 times 1/millionth of the lunar mass. Well, this translates to, as it says here, a spherical nickel iron object about 100 kilometers in diameter would be a rough equivalent.
That's a bruiser of an impact.
Well, yeah. So a spherical nickel iron object, 100 kilometers, that's 60 miles in diameter. So what they're saying is that it looks like a 60-mile diameter, something extremely dense, is embedded just below the surface of the moon.
Now, is that from an impact? Is that from an impact, or is that from something else? How is that there?
How is that there? Well, let's go on. Does each of these Mascons represent an asteroidal-sized body which caused its associated mare by impact? If not, simply the original impactor itself, by what processes were they formed in the lunar interior? Is the presence of these objects consistent with a molten lunar interior? Well, if it's molten, let's go on here and dive into some of the physics of it here. I'm going to show you a map of, this is a lunar gravity map. Contour lines show the gravity strength above the mean value of the moon in units of 100 milligals. Right, so this is the near side, and each of these is a Maria. Yeah, there we go with the labels: Mare Imbrium, Mare Humorum, Mare Serenitatis, Mare Crisium, and Mare Nectaris. If you would be so kind, would you pull up maybe a high-res photo of the moon? So here's Mare Imbrium, this really big one, Mare Serenitatis, Mare Crisium right over here on the edge, Mare Tranquillitatis here, Mare Fecunditatis there, and there's Nectaris. So we got them labeled right. We just didn't have them all. There's Mare Nubium, Mare Humorum. This is Oceanus Procellarum and Mare Imbrium. So there we go. Those are the Mare, and they're almost all on the near side. Let's see. There's one on the back side. I don't know if I have that. There it is, right here. So if these were produced by bombardment, which presumably they were, this seems like it would have been a large flux of objects, very large objects, slamming in to the near side of the moon. Now that's interesting to think about. How do you explain that? And if it's the near side of the moon, then if there was a large flux or a flux of these large objects, approaching the moon and slamming into the moon with this concentration of impacts, because presumably, what do we got here? 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 8, and then that's probably 9 if you include Oceanus Procellarum. Well, now we're talking about 9 huge objects coming at the moon, assuming that all of the collection of these objects moving through space didn't all hit the moon, right? There must have been objects that flew by the moon without striking it. But that means if it's the moon's lunar face towards us, well, then that means that the Earth itself would have had to have been in the pathway of these objects, right?
Right. And those would be, you wouldn't think that those would be oblique angles. Those would be straight on because of the formation of the craters, the way they're set. You wouldn't think it would be because you would have a round impact and then a dispersion as opposed to round impact sites. So you wouldn't think that they're coming in at strange or odd angles. Those look like direct hits. If they're caused by impact events.
But if they're not caught, well, then what could they be? I mean, you would think that the Mascons, well, do we assume that those are the remnants of large impactors?
That's the current version that I've heard. I'm not sure if it makes sense.
Well, and here's this, like this is one of the Mare Serenitatis. Serenitatis, yes. And you can see how shallow it is. Right?
Yet there's what below the surface of some of these? We're talking 60 or 100 kilometer wide.
Yeah, so that's 60 miles being a rough equivalent. Not necessarily being a rough equivalent.
It's 100 kilometers.
Doesn't necessarily mean that it's spherical, but that's what they're saying. That's rough equivalent would be a sphere. Up to 60 miles in diameter of some dense material. But
and
let's
again,
go on with it because it is. Okay, so let's see here.
And again, you've got that dense material in one, consolidated in one space. You have the assumption of something that is the equivalent of a 100 kilometer sphere of nickel. The density is not 3.4.
Nickel iron.
Nickel iron.
No. The density of nickel iron. While I'm getting us back to where we were, pull up nickel iron. And let's see. I mean, that's got to be what? 6, 7?
So it's 8.94 is nickel. So let's see what it is with nickel iron. 8.7 for a nickel iron alloy.
Okay, so that's much more dense than the moon itself.
So at 8.7 grams per cubic centimeter, that way offsets the 3.46 assumption.
Yes.
Being homogeneous. It'd have to still be homogeneous. It's not even taking into account 100 kilometer wide effectively.
Right.
So where's the mass? That's what we're asking. It's like little old lady in the Wendy's commercial. Where's the beef?
Where's the beef?
So here's the vertical acceleration at the lunar surface for the LP165P gravity field. Accelerations are the radial component at the lunar reference sphere with radius 1,738 kilometers. The near side on the left includes coefficients to degree and order. The far side on the right displays terms to only 1 degree and order 60 in order to limit noise in the image. Anyways, well, there you can see that the mare are concentrated on the near side. They're associated with mare, which we just saw are all concentrated on the near side, which creates quite a remarkable differentiation between the two sides of the moon. So then after that, there's some commentary here by J. Gordon Stipe that was published in the journal Science in 1968, probably, right after Muller and Sogren's paper. And this is what he says. The discovery by Muller and Sogren of Mascons in the moon is of great interest. My investigations allow a calculation to be made of the size and depth of the Mascons in terms of the size of the mare formed by low velocity impact of an iron meteorite. And of course, it would have to be low velocity, because if it was not low velocity, the object's going to vaporize. Okay? He says, I'm currently completing an analysis of penetration and cratering of concrete and soils by steel projectiles. I shall extrapolate these relations to craters the size of the largest lunar mare. This involves extrapolation from the largest craters in concrete, about 2 meters in diameter, to mare a few hundred kilometers in diameter. Ronka described the possibility of magma formation by cratering. And his figure 1 can be used to find the depth of penetration in the Earth needed so that the resulting pressure release at this depth would lead to melting. Because, as you go down in depth, the temperature goes up. But what prevents the melting is the overlying pressure. So if you remove that pressure, let's say through an impact event, you now have this pressure relief melting. The material, the magmatic material then will upwell. This is typically why, for example, some geologists have proposed that the Yellowstone mantle plume might have been formed by a large impact of a rapidly moving iron object coming in relatively perpendicular to the Earth's surface at the point of impact, being able to punch a hole right through the upper crust and exposing the mantle. The upwelling of the magma plume was then the result of this pressure relief melting. So he goes on here to say, let's pull it up here. These results suggest that the lava-filled mare were formed when very large iron objects struck the surface of the moon at a velocity so low that there was no immediate fracture of the object. Now, how do you explain that? It's moving so slow. The impact produced a very large crater, and the object penetrated to such a depth that deep material was melted by pressure release and flowed to the surface to fill the crater. The interior of the moon must have been solid when these events occurred, because otherwise the dense iron meteorite would have sunk into the molten material. Does that make sense? If the interior of the moon is molten, and you've got this
8.7 grams per cubic centimeter. Yeah.
8.7 grams per cubic centimeter. That's not going to sit there on the top of molten material. It's going to sink into that molten material. And it's going to keep on sinking until either it melts or it comes to a density roughly equivalent to the density of the object, at which point it would cease its descent towards the gravitational center of the moon. So what that's telling us is that the interior of the moon must have been solid and not molten when the mare formed. Now, okay, now we're trying to square that with interior volatility of the moon. Remember, there was something else we learned in our last episode. I think we were talking about the echo phenomena in the moon.
The moon rings like a bell.
The moon rings like a bell. Yes.
So
the scattering.
It kind of contradicts with this current theory.
Well,
that the moon would be solid.
Well, let's keep going here. The suggestion by Muller and Sogren is very reasonable. However, The depth of the Mascons, which they take as 50 kilometers or 30 miles, seems to be considerably underestimated. The depth of an impact crater measured to the bottom of the shattered material in the crater is approximately 1/4 of the crater diameter. This means that if the Maria are filled craters, then the depth of Imbrium, for example, is about 300 kilometers, and the depth of Humorum is about 100 kilometers. Or in other words, 180 miles or 60 miles. Those are some really damn deep craters. Because how wide is Humorum? Well, if it's 4-to-1, then Humorum has got to be 1,200 kilometers wide. And the depth of, Imbrium, not Humorum, Imbrium would be 4 times 300 kilometers or 1,200 kilometers wide, right?
Yep.
And given, so anyways, if the Mascons are deeper, as I suggest, then they must also be more massive to produce the observed gravity anomalies. Because the deeper they are, the smaller is going to be the gravity anomaly. If
Correct.
you took that mass all the way to the center of the moon, there would be no gravity anomaly.
It'd be a homogeneous mass at the center of the moon, as opposed
Right.
to a Mascon.
As opposed to a Mascon, yes. All right. I'm perplexed here. So 300 kilometers, that's, like I said, that's 180 miles deep. Given the assumed size of the impactor and the width of Imbrium. Yet the damn thing is only about 4 miles deep. So then the suggestion is that lava came out and filled the crater. Okay, well, if the impact, but here's the problem as I'm seeing it. If the impact is able to produce that much lava, and I mean, we could calculate the volume of lava if it's filled that whole crater, wouldn't that completely destroy the impactor itself as well?
You would think it would actually reduce the amount of concentration of mass, because you're going to have a hot ejecta.
Yeah. Yes.
That's going to consume the nickel iron impactor.
Consume it. Yes.
So, and again, none of this squares with a 3.8 grams per cubic centimeter homogeneous mass
Right.
for the moon.
Okay, so then also we have the journal Science was running, this was, a lot of these lunar results were new at the time back in 68. So this is by John A. O'Keefe. He was a lunar scientist back then who worked on the program. And he's talking about this work of Miller and Sogren. So Miller and Sogren have performed the astonishing feat, let's go here, of providing a relatively detailed, though preliminary, gravimetry of much of the front surface of the moon. The data from which they worked is in no sense marginal. The perturbations of the orbiter satellites which they used are so large as to have been an operational nuisance before they were understood. The interpretation suggested to Muller and Sogren by the papers of Harold C. Urey and tentatively adopted by them attributes the mass excesses in the Mare regions to mass concentrations, perhaps remnants of colliding iron asteroids of the order of 100 kilometers in diameter buried under the lunar surface. However, we got a problem there. On the other hand, both observation and experiment indicate that impact at normal meteor velocities leads to the scattering of the impacting mass as a result of shattering and vaporization. So normal meteor velocities, an impact at normal meteor velocities leads to a scattering of the impacting mass as a result of shattering and vaporization. Even if it is supposed that the circular mare were made by bodies already in orbit around the Earth, and hence having relative velocities of only a few kilometers per second, there remains a difficulty in supporting the mass. The pressure exerted by such a body on its base would be on the order of 8 kilobars, or 110,000 pounds per square inch. This exceeds the crushing strength of granite. It is reasonable that a mass of this kind would crush its way to the center of the moon. The analogy I've kind of used is, imagine you have a bowl of pudding and you have a lead bullet, and you place it on the pudding, and it's going to slowly sink right to the bottom of the bowl, isn't it?
Yep. Or shoot it at the bowl of pudding and see what happens, or throw it at least.
Well, then
It's moving fast.
right. But in this case, they're trying to slow it down so slow that there's no shattering of the object. And he's saying here that even a couple of kilometers per second. I mean, what's kilometers per second? A kilometer per second, you're looking at 3,280 feet per second times 3,600 gives you a lot of feet. Let me divide that by 5,280. And you're still talking over 2,000 miles per hour. So the object, even at 2,000 miles per hour, boom, it's going to shatter, and the mass of the impactor is going to scatter because of the shattering and vaporization. And the end result would be no Mascon.
Correct.
So how do you do that? How and if it didn't shatter and remained intact, well, then it would, given 110,000 pounds per square inch, this exceeds this. I mean, this is way beyond what would cause granite to completely crush. So then it says it is reasonable that a mass of this kind would crush its way to the center of the moon.
I don't think this model of an asteroid impact creating the mares is a good model. Doesn't seem to pan.
Yeah. Well, let's refer back to the paper by Harold C. Urey, which was also published in Science, 1968, and in December of 1968. Muller and Sogren have concluded that there are very massive objects in certain locations at the surface of the moon. These mascons, as they are called, represent a non-isostatic condition in the surface of the moon. Let's pause there for a second. Remember, isostatic is the vertical adjustment of a body. Earth, moon, doesn't matter. This is saying it's a non-isostatic condition, because an isostatic condition would require that these objects, like we just learned, should descend towards the moon's center of mass. These mascons represent a non-isostatic condition in the surface of the moon. If the Mare Imbrium situation is taken as a prime example, because it exhibits a maximum effect, we come to the conclusion that the viscosity of the moon must be higher than that of the Earth by a factor of 10 to the fourth. In other words, 10,000 times higher than that of the Earth. It is difficult to devise a lunar history which provides the low temperature required to account for the lack of isostasy and the low electrical conductivity, and at the same time for melting processes required to produce the basaltic material on the surface of the moon. So the viscosity of the moon must be higher than that of the Earth by a factor of 10 to the fourth power, which is 10,000. 10,000 times greater than the viscosity of the Earth.
There comes that several orders of magnitude denser outer surface of the moon than the Earth.
Yeah. Now, let's jump forward 11 years to 1979 after additional data and more studies have been conducted on Mascons. This is by A.E. Ringwood in the textbook Origin of the Earth and Moon. This is what he says. At one time, it was naively believed that Mascons are remnants of the dense projectiles responsible for the excavation of the basins. But it was soon realized that they would have been totally vaporized. Furthermore, the largest Mascons only occur in those basins which were filled with mare basalt. But if Mascons are simply layers of mare basalt lying on top of low-density crust, how was this excessive mass brought to the surface of the moon in the first place? Right? Because if it's something to do with the layers of basalt, and that's where the density origin is, and that's lying on top of lower density crust, you're now talking about you've got to bring higher density material up to the surface of the moon, which is the exact opposite that lower density material higher density material should be migrating towards the center of the moon, especially if the moon is molten. Well, goes on to say, if a planet is in isostatic equilibrium, the overburden pressure will be constant at any given distance from the center of the planet, which we presume is like more or less the case with the Earth. Terrestrial continents are much thicker. Terrestrial continents are much thicker than the oceanic crust, simply because granitic type rocks have lower density, right? So the lower density rocks are rising up, the higher density rocks are sinking down. The large Mascons of Imbrium and Serenitatis would certainly not have survived on the moon in isostatic equilibrium. They would have sunk without a trace. Perhaps the most remarkable aspect of Mascons is their very survival. The fact that they still exist today implies that the moon's crust must have been remarkably rigid for a very long time. Remarkably rigid. So then we're going to go...
Remarkably, being 10,000 to 100,000 times more rigid than the Earth.
What it's looking like. Now I'm going to jump all the way back to 1962 in the work of Gordon J.F. MacDonald. Was published in the Journal of the American Rocket Society, the journal called Astronautics. The title of the paper is The Moon and Its Interior. So, this is quoting now from Gordon J.F. MacDonald. Data relating to the lunar interior have been derived from astronomical observations. These data fix the mean density of the moon and provide an estimate of its gravitational figure. Now, this is before the discovery of Mascons. The mean density is well established at 3.34 grams per cubic centimeter. This value is tantalizingly close to the density of a large number of silicate materials found on or near the surface of the Earth. Yet, the mean density of the moon presents a number of major problems. The abundance of the radioactive elements determines the internal temperature distribution of a planet. Urey, in 1952, pointed out that a limit on the possible temperature distribution within the moon can be derived by an indirect argument using the moon's gravitational figure. If the temperatures within the moon approach the melting point of the silicates, then the figure of the moon should closely approximate that of a fluid with an equivalent density distribution. Got it? Let's go. If the temperature within the moon approaches the melting point of the silicates, which, given the mass of the moon, it should easily approach and exceed that melting point of silicate rocks, right? Which he's citing this because they have roughly the same density as the moon as a whole, 3.34 grams per cubic centimeter. The physical librations of the moon provide an estimate of the ratios of the difference in moment of inertia to the mean moment of inertia. The ratio of the difference in the moments of inertia to the mean moments of inertia are much larger than would be predicted for a homogeneous moon in hydrostatic equilibrium. So look up moment of inertia. Let's define that for the listeners and also for our own clarification. I usually will use an example of, and it's an approximate example, but I will use oftentimes in lectures I'll say, okay, here's one way to help understand it. Let's say we have a line here, and that is a diameter of a spherical object, and it's radially symmetrical about its center of mass. Its moment of inertia would coincide with its center of mass, and what that means is from an exterior view, looking at a gravipotential map, this would appear the equivalent of a mass point, right? So if you're trying to turn this axis, this diameter, axial diameter, and it's only one point, it's easy to turn. Like what I'll do is I'll hold something up, I'll tell somebody, here's this pencil. Hold this pencil, pinch it as hard as you can, and prevent me from rotating it. Well, nobody can do it. But then if I say, hold it in 2 points, now I'm going to try to rotate it, and you resist my efforts to rotate it. Well, now it's a completely different matter, right? In effect, you can kind of think of this as one moment of inertia and 2 moments of inertia, okay? So there's a difference between the mean moment of inertia and the actual moment of inertia. Now, what did you come up with for a definition there?
So the moment of inertia, also known as the mass moment of inertia, angular rotation or mass, second moment of mass, or more accurately, rotational inertia of a rigid body, is defined relatively to a rotational axis. It is the ratio between the torque applied and the resulting angular acceleration about that axis.
There we go. That's what I'm talking about. The torque, which is this, you apply a torque. So what's happening here is the Earth's gravity field is exerting a torque on the moon. But we know something about the moon's rotation on its axis, don't we? It's perfectly synchronized with its orbital period. All right? So going back to Gordon MacDonald's article, the ratio of the difference in the moments of inertia to the mean moments of inertia are much larger than would be predicted for a homogeneous moon in hydrostatic equilibrium. He goes on to say, like the Earth, the moon is flattened at the poles and has a bulge all around its equator. Unlike the Earth, the moon also protrudes along the direction between the center of the Earth and the center of the moon. Picture moon, picture Earth, draw a line from the center of the Earth to the center of the moon, and it protrudes along that line. There is thus an additional bulge on the side of the moon that always faces the Earth, and on the opposite side. If the moon were fluid and acted like a putty-like plastic, then the very slow rotation of the moon should produce an equatorial bulge all the way around uniformly, like we see in the Earth. But the equatorial radius should only be 50 meters greater than its polar radius in the moon. Now in the Earth, which is spinning much faster on its axis and has much greater mass, that difference is 13 miles between polar diameter and equatorial diameter. However, in the case of the moon, the measured equatorial radius is 1 kilometer greater than the polar radius. So similarly, the gravitational attraction of the Earth on the moon should pull the moon out by 40 meters. But the actual protrusion toward the Earth is more than a kilometer. So if we take a kilometer being 1,000 meters, 40 meters is 1/20th of that. So in other words, that bulge is 20 times greater than it should be just based upon that alignment, or relative to what the bulge should be, right, around the equator. But it is not radially symmetrical about the equator. It's got this bulge that's in line with the Earth. So it would appear that the Earth's gravity field is somehow locking into that bulge alignment. And this is what's keeping that 1-to-1 spin orbit coupling between the Earth and moon, that gravitational lock between the Earth and the moon. So, in conclusion, he says, similarly, the gravitational attraction of the Earth on the moon should pull the moon out by about 40 meters. But the actual protrusion toward the Earth is more than a kilometer. The difference between the shape of the real moon and that of an ideal plastic moon indicates that the moon has great strength. McDonald goes on to say this: the astronomical data on the rotation of the moon suggest that it is a relatively strong body capable of supporting stress differences comparable in magnitude to those supported within the Earth. If a major fraction of the moon's interior were molten or nearly molten, the distorted figure of the moon could not be supported. Astronomical data can also be used to obtain an estimate of the distribution of density within the moon. If the astronomical data are thus reduced, it is found that the data require that the interior of the moon be less dense than the outer parts. Indeed, it would seem that the moon is more like a hollow than a homogeneous sphere. This suggests that there are inconsistencies either in the reduction of the observations of the moon's motion or in the numerical development of the lunar theory. It seems more acceptable to assume that there's inconsistencies in the observations of what the moon is actually doing or in the numerical development of the lunar theory, rather than accept the idea of a hollow moon. However, we don't want to stop there because I think this is an oversimplified version, right? But the point is, the idea of a hollow moon suggests the considerable absence of mass within the moon. Then we're going to go back to John O'Keefe, and this is what he says. This is 68. Isostasy on the moon. To study the effects of internal variations in density on the gravitational field of a body, the first step is to remove the effects of the visible topography. This correction is known as the Booger correction. The resulting chart of Booger anomalies obtained by applying the Booger correction to the anomalies found by Sogren and Muller is shown. The fact which leaps to the eye is that the Booger anomalies are much larger in both directions than the anomalies determined by Sogren and Muller. In the 18th century, a similar situation was noted in the Andes Mountains of South America by Booger himself. It is as if the topography were massless. And in fact, Booger suggested that the volcano Chimborazo might have enormous caves. Let us consider that the possibility that the lunar matter is highly porous. He's using Chimborazo, the volcano, as an analogy and suggesting that the apparent absence, the low density booger anomalies suggest enormous caves. Well, what do we appear to have confirmed within recent years?
Large magma tubes or lava tubes in the moon. And a significant tunnel network interconnecting.
It's what it's starting to look like. It's starting to look like you have some kind of a lunar core. Of what it consists is still an open question. You've got this extremely rigid shell near the surface of the moon, and in between those two, you have this porous material. Now, how does that come about? Now, we're going to try to slug our way through this. This is V.A. Fursoff in 1969, the book, The Old Moon and the New, and he's wrestling with this idea, right? He says the ratio of the surface area to the volume of a sphere increases in inverse proportion to its radius. Okay? So, in other words, it's inverse. So, increase the radius of a spherical body, and the surface area to the volume increases in inverse proportion. Thus, the surface area of the proto-moon will have been 10 to 15 times larger in relation to its volume than that of a proto-Earth. So in other words, the smaller moon has a larger ratio of surface area to its volume. And compared to the proto-Earth, it's going to be 10 to 15 times larger. Okay? So, other things being equal, the generation of radioactive heat will be proportional to the volume. Right? The greater volume, you're going to have greater radioactive heat being generated, which is going to migrate towards the surface and then be discharged out from the surface. Right? Other things being equal, the generation of radioactive heat will be proportional to the volume, while its loss by radiation will be proportional to the surface area. So the amount of radiation is going to be proportional to the volume, but when it reaches the surface, the loss through radiative output from the surface is going to be greater. So because of that greater loss of radiation from a volume the size of a moon, the moon would thus be cooling 10 to 15 times faster. Okay? So under high gravity conditions, the volatiles will be squeezed out to the surface much more effectively. But under low gravity, gravitational fractionation will generally be less effective. So then, because the fractionation is going to be less effective, the migration to the surface is going to be slower. Yeah, the ascending volatiles will be chilled. They'll have an opportunity to cool in approaching the surface layers. So the volatiles will continue to expand upwards, insinuating themselves into any weaknesses they may encounter. So here now could be the origin of our vast network of lunar tubes. Fursoff goes on to say this: the result will be a honeycomb of gigantic cavities. From this, it will be seen that the differential pressures at the base of lunar mountains and even the whole of the geometrical bulge will make little call on isostatic adjustment and may be wholly absorbed by the structural strength of the rigid honeycomb crust. Without any claim to finality, let us consider a three-layer model in which the core is surrounded by a SIMA, which is a silicon magnesium material, of mean density 3.30, sheathed in a peel of light porous rocks with a honeycomb of caves permeated with volatiles and having an average bulk density of 1. So here we're kind of coming with a model. What appears to be perhaps a dense core, but in between that is this honeycombed structure that is extremely rigid, supporting an equally rigid outer crust of the moon. Rigid enough that it's supporting the Mascons. Whatever the hell those Mascons are, they're sitting there like lead pellets sitting on top of the pudding that's not migrating down to the bottom of the bowl. Because whatever is under it is so rigid and supporting it. And so, where is this bringing us? So this is from 1972, Lunar Research. No agreement on evolutionary models. New and in some instances, surprising results from experiments on Apollo 14 and 15 and on the USSR's Lunar 16 were presented at the third Lunar Science Conference a few weeks ago, and interpretations of the data provided additional perspective on the earlier findings from Apollo 11 and 12. In comparison with earlier conferences, a far more comprehensive picture of the moon, but far fewer claims to understand how the moon evolved, were evident. Independent evidence from several types of experiments indicates that the moon is now a relatively cold and inactive planetoid, but that it has had a complex thermal history. There is an apparent conflict between geochemical evidence that suggests an initially cold moon, in which partial melting of its outer layers took place, and magnetic evidence that seems to indicate an initially hot moon with a molten core. So, the existence of a layered crust and the apparent differences in composition in the two layers are evidence that the moon has undergone differentiation. Obviously, if you've got this rigid crust and then a honeycombed interior under it, are evidence that the moon has undergone differentiation and that the layers were formed at different times. The seismic evidence thus appears to agree with the hypothesis based on geochemical data that a moon-wide crust was formed from early melting of an aluminum-rich material, and that this original crust was partially covered by the outpouring of lavas which formed the Maria. So where are we with this? I don't know. I don't know the answer. I can't explain it.
No
Now,
consensus yet.
No, and you know, in terms of the giant Mars impact hypothesis, how does that square with the kinds of anomalies we've been exploring here? How does an impact that you'd think would be, okay, an impact is going to create, first of all, a ring around the Earth of debris between the proto-Earth and this Mars-sized body. Somehow you have to get from that dispersed ring into a single object. And that single object now needs to have the attributes and properties of the moon as we've been exploring here. So let's talk about the giant impact hypothesis for a minute. This is from a couple of astrophysicists. This article appeared in the journal Icarus in 1996. The title of the paper was Accretion of the Moon from an Impact-Generated Disk. Let's go over here. The giant impact scenario proposes that the impact of a Mars-sized protoplanet with early Earth ejected enough material into Earth orbit to form the moon. The impact scenario has become the favored explanation for lunar origin in the past decade, as it can potentially account for all of the major geochemical and dynamical characteristics of the Earth-Moon system, and it still is the preferred explanation. The system's high angular momentum, the depletion of volatiles in the lunar material, which of course would be a consequence of the extreme temperatures of the impact, the bulk similarity of lunar material to pre-differentiated mantle, lunar iron depletion, and lunar density. Okay. We present the first published numerical calculations of acceleration of an impact-generated proto-lunar disk into a single large moon. Previous numerical simulations of a large impact event predict that the formation of a disk of material centered near or within the Roche limit. Let's pause right there. What's the Roche limit? The Roche limit, you could look it up. I'll try to give a layman's explanation of it. It's a zone within any gravitational field whereby an object passing through that zone, the gravitational force exerted on that object will overcome the coherence of the material forming the object, causing it to disaggregate. If you found now what have you found for Roche limit?
So the Roche limit, also known as the Roche radius,
Sure,
is the distance from a celestial body within which a second body held together solely by gravity will disintegrate due to the first body's tidal forces exceeding its self-gravity.
There we go. That's what I was trying to say. Okay. And we saw that. We witnessed that happen with Shoemaker-Levy 9 in 1993-94, because that you had a single comet nucleus which passed within the Roche limit or Roche radius of Jupiter. The gravitationally induced tidal forces of Jupiter caused the disaggregation of the single nucleus of Shoemaker-Levy 9 into 21 separate objects, right? So this is what we're talking about, the Roche limit. Okay, so now applying that concept, the Roche limit, to this ring of debris that is now orbiting around the Earth, okay? So previous numerical simulations of a large impact event predict the formation of a disk of material centered near or within the Roche limit, which is roughly 2.9 Earth radii. A natural expectation based on our previous results and comparison with the satellite systems of the outer planets would be for multiple small moons to arise from such a proto-lunar disk. Our calculations, which include both moonlet accretion and orbital evolution, demonstrate that forming massive moonlets in the inner disk near the Roche limit is extremely difficult. We conclude that an Earth system with multiple moons is the final result, unless some particularly severe constraints on initial conditions in the disk are met. So he's pointing out the problems there with the whole, this is what the mathematics suggest, is you're not going to get consolidation into a single object. What you're going to get is you're going to get a disk with a bunch of smaller objects that will accrete, moonlets that he's calling. And that, to me, has always been the major problem with that particular theory. It explains other things, like it said here. It explains the system's high angular momentum, its depletion of volatiles, the bulk similarity of lunar material to pre-differentiated mantle, I presume Earth mantle, I'm guessing, lunar iron depletion and lunar density. I'm not sure how it would apply to lunar density, but in any case, the mathematics suggests that that was going to be a very difficult problem to somehow aggregate that disk of demolished material, which undoubtedly must be millions of pieces of fragmented stuff, both the impactor and the Earth itself, to get from that into what we're been talking about here, the moon as we now know it, with all of its inexplicable anomalous phenomena associated with it. See? And I think it's kind of like more or less similar in some ways to like, oh, the Missoula, okay, we've got a large proglacial lake. Good, we've got an explanation now. We don't need to, we can set all those anomalies and inconsistencies aside for now. I think that we kind of see that kind of a psychology playing out here, perhaps. So, where does that leave us? Well, it leaves us that the moon, in fact, I was looking for the quote here, but the moon has also been described as being more like an inside-out planet. But apparently, I think we're honing in on a model of the moon as being, well, if you will, almost honeycombed with large caves, which is interesting. Let's go through what we have just, some of the things, the anomalies. The lunar orbiter has produced unexpected results. Very massive objects in certain locations at the surface of the moon. Very large mass concentrations beneath the center of all 5 near-side Maria. A spherical nickel iron object about 100 kilometers in diameter would be a rough equivalent. These are all quotes extracted from the articles we've just gone through. A mass of this kind would crush its way to the center of the moon. Our initial assumption of a homogeneous moon cannot be true. There's a drastic distinction between the different phases in the lunar interior. A great deficiency of mass in the uppermost layers of the lunar globe. The moon is more like a hollow than a homogeneous sphere. It is as if the topography were massless and, in fact, might have enormous caves. The result will be a honeycomb of gigantic cavities. The structural strength of the rigid honeycomb crust becomes a useful analogy for the moon, given now, you know what's interesting about this, and I think that this is where we're going to have to leave it for this episode. But let's look at the next. What is this we're looking at, John?
I don't know, Randall. What is this?
It's a Masonic apron. Typically, this one is probably from the late 1700s, early 1800s. And it's a what should I say? It is a story written in symbolism. And all Masonic lodges throughout the world have held the symbolism of the beehive in high esteem for some reason. And I'm not necessarily suggesting anything here, but they must have had a reason, because there's nothing here that's not meaningful to the whole composition and the meaning that's extracted from the whole composition. So anyways, I think maybe we leave it there for now. And we'll just see how far we dive into ancient traditions about the moon, or do we move on?
Tell us in the comments section. You want more on the ancient traditions of the moon, or what would you like Randall to cover next?
Okay. Well, I'm open. You know, I've been kind of indicating I was going to talk about the moon at some point in greater depth. I certainly don't have the final answers. I'm not going to sit here and pretend I'm gotten to the bottom of all of this. What I think we are doing, though, John, is we're raising legitimate questions. And probably, it appears to me, approaching the necessity for what William R. Davis, the founder of geomorphology, called the outrageous hypothesis. So maybe we will leave it there for now. I think there might be some dinner waiting for me.
Ooh.
We've
Bon
done
appetit.
a good, hour and a half here, 90 minutes or so?
Yep.
Good. Well, I want to thank everybody who's joining us and who was able to hang through this. I know it got a little technical. We're all learning together, and I hope you look at it that way, that I'm not trying to present myself as any final explanation for anything. I am really more trying to raise questions and point people in the direction of some very interesting areas to look at closer, right? So that's kind of where we're coming from here. And I want to thank you, John, for being such a great sounding board and help in these investigations into the mysteries of our life on Earth, which of course includes our nearest celestial neighbor, the moon, which we know, without which we would probably we'd be sitting here two slugs right now. Because we never would have gotten out of the ocean without the moon, right?
We need the moon.
We need the moon.
It's taken a lot of slugs for us.
Yeah.
If you look on the far side.
No pun intended, right?
Mm-hmm.
So, it's starting to appear like somebody thought this out. Somebody thought this through,
Interesting.
All right, John. Thanks much. See you next episode.
Yes, sir.